Hi everyone, in this video we're going to be talking about what's called the characteristic equation. But first let's review some things. So recall what we've learned previously. X is an eigenvector by definition if, when we say we have a matrix A times X, it equals some scalar lambda times X, as long as X is not 0. And then the scalar lambda, we call that an eigenvalue. And then the set containing X, or all possible X's, is what we call the eigenspace of our matrix A, corresponding to that eigenvalue lambda. And so that's true if A minus lambda I times X equals 0. All right, so we've done this before, but let's take a look at this example. Find the eigenvalues of this matrix A. So what we're trying to figure out here is non-trivial solutions to this equation right here. A minus lambda I times X equals 0. And so we have A, our matrix A, and then remember I is just your identity matrix. So lambda times I in the case of a 2 by 2 just looks like this. And so this result right here, this is A minus lambda I. And then now remembering some other things we've learned before, A is invertible means that the null space of A contains only 0. Okay, the set contains 0 only. So then A times X equals 0 if and only if X is 0. All of this is to say that this is the trivial solution. Okay, X equals 0 is a trivial solution to this equation right here. And so if that's true, if A is not invertible, then there exists a non-trivial solution. Okay, so we wanted to remember what it means when A is invertible so that we could say if it's not invertible, then there exists a non-trivial solution. Also, we've learned before that the determinant of A is not equal to 0 means that A is in fact invertible. And so if the determinant of A is 0, then A is not invertible, and there exists a non-trivial solution. Okay, so picking up with this example again, we want to now find lambda such that A minus lambda I is not invertible. So another way to say that is find A minus lambda I such that the determinant of it equals 0. All right, so now we just do some computation here. So we have A minus lambda I as a matrix here, but if we write it as a determinant, remember all that changes is these vertical lines. When it's in matrix form, it has these brackets instead. And so the determinant here, we want it to equal 0. And so it's just a 2 by 2. So this one's pretty nice. Remember, it's just diagonal down right minus diagonal down left. That's why we have this here. After a little bit of simplifying and rearranging, we get lambda squared plus 4 lambda minus 21 equals 0. And then we're just solving for lambda. In this case, we can factor. If you find that you can't factor this, then you could try using a quadratic formula if it's a quadratic equation. And we get that lambda is -7 and lambda equals 3. All right, now let's remember some things about determinants that we've seen before. So 4 facts that we've seen actually in the past, but just reminding you. If the determinant of A equals 0, A is not invertible. If A is invertible, then the determinant of A is actually the products of the diagonal entries, as long as it's in triangular form. But we've done this previously, and I want to remind you, if you have to get to triangular form by doing some row operations, remember that that can actually affect the determinant. So if you do any interchanging of rows, let's say you interchange rows a total of r times to get to triangular form, then the determinant of A is actually -1 to the r power times the determinant of the result you got once you got to triangular form. And then also, if in the process of going into triangular form, if you have to scale a row, so multiply a row by a number k, then your determinant A is actually the 1 over k times the result that you got, or the determinant of the triangular form matrix that you got. And then number 3 here, the determinant of the product of two matrices is equal to the individual matrices determinants being multiplied. And then if you're talking about transpose of a matrix, the determinant is equal to the original matrix. Okay, so we've done these in the past, but I wanted to remind you about those. And now also something we've seen before, and this is pretty long and we've added to it a few times, is the invertible matrix theorem. So This is a pretty good theorem to keep on reference, just having all these components available to review, because all of these are true at the same time, or they're all false at the same time. So if A is invertible, then it's equivalent to an identity matrix, and so on. So this is parts A through K. And then all the way up to part R, A through R are all either true at the same time or all false at the same time. And then why we're bringing this back up now is because we're going to add two more things to it. So adding to our list for this invertible matrix theorem, we can now say that the number 0 is not an eigenvalue of A, and meaning all these other things are true if that's true. So basically lambda cannot be 0 if A is invertible, and the determinant of A is not 0. All right, so two more parts to add to our invertible matrix theorem. Now, the title of the section was characteristic equation, and here it is. So the scalar equation, where we have the determinant of A minus lambda I equals 0, this is what we're calling the characteristic equation of our matrix A. And so a scalar lambda is an eigenvalue of an n by n matrix A if and only if this lambda satisfies the characteristic equation. Okay, so let's try this out. We're going to find the characteristic equation of this matrix, this 4x4 A. And so what we're trying to do, because we want the characteristic equation, we are interested in the determinant of A minus lambda I. But just remember that lambda I is going to just be lambda times the ones in the diagonal of the same size matrix. And so when you subtract A minus lambda I, it's going to basically look like minus lambda down the diagonals here, just like we have on this one. Okay, so we want the determinant of this matrix. And in this case, it's already in triangular form, so we can do this determinant very quickly. It's just the product of the diagonals. But a quick reminder, if your matrix is not in triangular form and you want the determinant, you can do two things. You can put it in triangular form by doing your row operations, but just be aware of how that affects your determinant, which we just reviewed. Or you can do your determinants the way we've learned them in the past, where you pick a row or column and you do your cofactor expansion. Okay, so in this case, we have it very nicely, just product of the diagonals. And so our characteristic equation is when this determinant of A minus lambda I equals 0. So all we have to do is set this equal to 0, and we call that our characteristic equation. And so in this case, I'm just giving you 4 versions of the same thing. So anytime you have a factor in common, you can go ahead and say that it's just that factor, in this case, squared. For us, we can go ahead and factor out a -1 from each of these products, and so we end up getting this result. Just a quick algebra note, this would be, there'd be like invisible -1 times -1 times -1 times -1, 4 -1s being multiplied in the front. So that's why it's positive. You don't see any sign in the front. Or if you do your foiling, if you expand this all the way out, you're going to get this result here. Okay, so these are all the same thing, and they're all the characteristic equation. They're just different formats for them. So in our case, if we go back to the factored version, for any of these factored versions, we can find the eigenvalues pretty quickly because this equals 0. So lambda equals 5, and that's a factor twice. So we call that multiplicity 2. It occurs twice in our equation. So we say lambda equals 5 has multiplicity 2. And then our other eigenvalues, lambda equals 3, lambda equals 1, each have multiplicity 1. They only occur once. And then in general, if A is an n by n matrix, then the determinant of A minus lambda I is a polynomial of degree n called the characteristic polynomial of A. So you could tell very much at this step why we say that. So this is a polynomial, and notice that it's degree 4, and our original matrix A was a size 4x4. All right, next let's talk about what's called similarity. So if A and B are n by n matrices, then we say that A is similar to B, and notice we are doing a math definition for the word similar here. If there is an invertible matrix P such that P inverse times A times P equals that other matrix B. Or the other way around is to say that P times B times P inverse equals A. Okay. So outside of math, you could say that two things are similar and you can have different criteria for how you classify something as similar. But in our case, similar in terms of matrices, this has to be true. Okay? So the invertible matrix has to exist, P. We have to be able to multiply one matrix by the inverse of P and P itself, like kind of sandwiching that matrix. And when we do that multiplication, we get the other matrix, and then vice versa. Okay, we sandwich the other matrix in between P and its inverse, and we get back to the first matrix. If those are true, then we can say that those two matrices are similar. Now, if, let's just say, we're going to rewrite this a little bit, Q, we're going to replace P inverse with it. Then what we have is Q inverse times B times Q equals A. And so B is also similar to A. And we just say that they're similar to each other. Okay, this note here is just letting us know that by definition, A was similar to B. And then by doing this little rewrite step, we're saying that B is similar to A. And therefore, they're just similar to each other. And then if we change A into P inverse times A times P, it's called a similarity transformation. So remember, the multiplication with matrices, the order matters. So by left multiplying it by P inverse, and then right multiplying it by P, that's what we're calling a similarity transformation. Or the same thing if we just do it this opposite way, P times B times P inverse, still called a similarity transformation. And then why we're interested in this idea of similarity is to get to this theorem. So this theorem says if n by n matrices, A and B, are similar, so basically before the comma of this theorem, we'd have to verify that two matrices are similar. And if we verify that they're similar, then we can go back to the theorem and say, well, then they have the same characteristic polynomial and the same eigenvalues with the same multiplicities. So that's the nice part about figuring out if two matrices are in fact similar. And then just one last thing to mention here in regards to similarity. For example, the matrices here, 2, 1, 0, 2, and 2, 0, 0, 2, they're not similar even though they have the same eigenvalues. So what I want you to take away from this one is that just because two matrices have the same eigenvalues, that does not imply that they're similar. You have to go back to the definition of similar and use the invertible matrix idea of multiplying on the left and the right to figure out if the matrices are similar. Also, similarity is not the same as row equivalence. So if A is row equivalent to B, then B equals, let's say, E times A for some invertible matrix E. Row operations on a matrix usually change its eigenvalues. So this is just saying that just because we have a row equivalent matrix, it doesn't mean that it's in fact similar. So if you're trying to figure out two matrices are similar, go back to the definition that we just learned about. And then once you know if they're similar, then you can use the theorem that we were talking about, that they have the same characteristic polynomial and same eigenvalues. Okay, so that's it for this one. Thanks for watching.